I'm Mirai Takematsu. I belong to Keio University, Japan. I will be giving a presentation titled QLearning based special reuse method considering throughput fairness by negative reward for high throughput. In special reuse method, wireless node try to use wireless resource efficiently by controlling both the transmission power and carrier sense threshold. When wireless nodes are densely developed, the special reuse method have difficulty to achieve both the high aggregate throughput and fairness because the mutual interference among the wireless nodes becomes severe. To solve the difficulty, the special reuse method using machine learning such as neural network and QLearning have been paid attention. In this study, we focus on QLearning-based special reuse. One of the challenges of QLearning-based method is to determine reward for both the high aggregate throughput and throughput fairness. So, in related work, the present to reward, selfish reward, and environmental reward. From related work, we can see that there is a room to improve the aggregate throughput with keeping throughput fairness among the nodes. Therefore, we propose a QLearning-based special reuse method considering throughput fairness for high throughput. The IEEE 802.11 standard implement carrier sense multiple access with collision avoidance to avoid the packet collisions. In CSMA, node perform carrier sense before transmitting packet to detect transmission from the other nodes. Specifically, the node detects the transmission if the received signal power exceeds carrier sense threshold. However, when the nodes are densely developed in wireless LAN, they have difficulty to utilize wireless resource efficiently even by CSMA. Specifically, they suffer from the following two problems in dense environments: the hidden node problem and exposed node problem. In the hidden node problem, packets of different nodes frequently collide at receiving node because they cannot recognize with each other by carrier sense due to the high CST of them or low transmission power. In the exposed node problem, nodes rarely send packet because they perform carrier sense accessibility due to the low CST of them or high transmission power of others. To mitigate the hidden node problem and exposed node problem, special reuse methods have been paid attention as the methods allow nodes to conduct adequate carrier sense using dynamic sensitivity control and transmission power control, DSC and TPC. Specifically, DSC allows nodes to change their CST. By increasing whenever possible the CST, the number of signals triggering by channel to be busy is reduced. Therefore, more simultaneous transmission will be allowed. On the other hand, TPC allows nodes to change their transmission power. By decreasing the transmit power whenever possible, interference to neighboring nodes are reduced. Therefore, more neighboring nodes will be allowed to transmit. Using this technique, the hidden node problem and exposed node problem is mitigated. On the other hand, the special reuse method have difficulty to conduct adequate DSC and TPC in dense environment because the mutual interference among nodes become complex. To solve this difficulty, the special reuse method using machine learning, such as neural network and QLearning, have been paid attention. By utilizing machine learning, the node can run adequate DSC and TPC without a lot of knowledge of the complex interference among them. In machine learning, the node can learn their control only by reward for the control in QLearning method. Therefore, we focus on QLearning based method. Therefore, next, I will explain QLearning. QLearning is one of machine learning methods, and the goal of QLearning is that agents learn optimal action by defining adequate reward. In order to achieve this goal, 3 operations are repeated in QLearning: select action and calculate reward and update QTable. First, agent select action. In this case, epsilon greedy strategy is often used. In epsilon greedy strategy, the agent selects their action randomly from the QTable with probability epsilon. In contrast, with probability 1 minus epsilon, they select the action with the highest expected reward among all the actions in QTable. Second, agent calculate reward. Reward is the index showing the quality of actions. Finally, agent update QTable with reward. QTables are composed of expected reward and action. Specifically, the QTable is updated from the following equation. The goal of QLearning-based specialist method is to define adequate reward for achieving both high aggregate throughput and throughput fairness. By defining the reward, node can learn adequate CST and transmission power by themselves. Therefore, next, I will explain how to calculate the 2 rewards presented in the related work. The first is the selfish reward. The selfish reward is calculated from achieving the high aggregate throughput. Although the selfish reward-based method improves the aggregate throughput, the method does not consider throughput fairness. As a result, the method allocates wireless resource to node unfairly. The second is the environment hour reward. The environment hour reward considers the minimum throughput in networks. Although the environment hour reward-based method can be allocated the wireless resource to the node fairly, the method has the limitation to improve the aggregate throughput because the reward is determined based on the minimum throughput in networks. Motivated by the above, we argue that there is a room to improve the aggregate throughput with keeping throughput fairness among the nodes. Therefore, we propose the QLearning-based specialist method considering throughput fairness by negative reward for high throughput. In the proposed method, wireless node learns the adequate CST and transmission power for the high aggregate throughput and throughput fairness by reward of QLearning. The main idea of the proposed method is that it distributes wireless resource of node with a high throughput among nodes with a low throughput. To distribute the wireless resource, the proposed method gives negative reward to the node with a high throughput. As a result, the node with a high throughput learns to suppress the wireless resource utilization by DSN and TBC. In contrast, the proposed method gives reward to the node with low throughput for motivating them to use the wireless resource actively. As a result, the node with a low throughput learns to obtain the wireless resource from the node with a high throughput by TBC and DSC, and they achieve both the high aggregate throughput and throughput fairness. The calculation of the reward is done from the formula in the green box. The 2 conditions are explained in the next slide. In the proposed method, the reward is negative when the following two conditions are satisfied. Condition 3 means that station I is in the top N station with the highest throughput among all stations. Condition 4 means that station I is in the top N station with the highest total throughput among all stations. At this time, N must be determined based on scenario. This time, we performed two types of simulation and we will explain them one by one. The first is a simulation to evaluate the influence of the variable N on negative reward. We deployed one station and one access point to each apartment, and station and access point were randomly placed in the apartment. We use aggregate throughput and chain fairness index as evaluation metrics. JFI is used to evaluate throughput fairness. The simulation parameters are shown in this table. Figure shows the aggregate throughput and JFI with changing N in the proposed method. The value of JFI increases as the value of N increases from 1 to 9. This is because the throughput of N stations are distributed among the other stations with the low throughput. As the value of N increases, the more stations with the low throughput can obtain the throughput from stations with the high throughput. As a result, the proposed method improves throughput fairness among all stations by increasing the value of N. In contrast with JFI, the aggregate throughput decreases as the value of N increases from 1 to 9. This is because the proposed method gives a negative reward to the N station for their high throughput. As a result, the aggregate throughput decreases as the number of N increases. These results indicate that there is a trade-off between aggregate throughput and throughput fairness. In this figure, when the value of N are 1, 3, and 9, the proposed method achieves the highest aggregate throughput balance between the aggregate throughput and fairness and the high throughput fairness. Therefore, we use 1, 3, and 9 as the value of N to compare the proposed method with the other method in the next simulation. The second is a simulation to compare the proposed method with the other method. The simulation scenario and evaluation metric are the same as in the first simulation. Moreover, the simulation parameters are shown in this table. We compare the proposed reward with the selfish reward and environmental reward. All method is based on QLearning and learn transmission power and CST. From the first simulation result, we use 1, 3, and 9 as the value of N to compare the proposed method with the other method. Figure on the left shows the comparison among the proposed reward, selfish reward, and environmental reward in terms of the aggregate throughput. Figure on the right shows the comparison among the proposed reward, selfish reward, and environmental reward in terms of the JFI. As shown in this figure, the proposed method with N equals 3 improves the aggregate throughput and JFI by 12.7 points and 2.3 points compared with the environmental reward-based method. Furthermore, in comparison with the selfish reward-based method, the proposed method with N equals 3 improved JFI by 23.4 points with slightly decreasing the aggregate throughput. These results indicate that the proposed method can achieve both the high aggregate throughput and throughput fairness compared with the other method by setting the adequate value to n. When the value of n is 9, the proposed method improves JFI by 31.7 points compared with environment-aware reward-based method. In the proposed method, a lot of stations received negative reward as the value of n increased. Therefore, throughput fairness increased as the value of n increased. In the environment-aware reward-based method, the minimum throughput in the network is given to all stations. On the other hand, all stations don't influence on the minimum throughput. Therefore, the reward contributes the throughput fairness to some extent. I'll summarize at the end. Recently, specialist methods using machine learning have been paid attention. In the related work of specialists using machine learning, we introduced two rewards, surface reward and environmental reward. However, there was a room to improve the aggregate throughput with keeping throughput fairness among the nodes. Therefore, we propose the QLearning-based specialist method considering throughput fairness by negative reward for high throughput. In simulation result, we have confirmed that the proposed method with n equals 3 improved throughput fairness and the aggregate throughput by 12.7 points and 2.3 points compared with environment-aware reward-based method. Here are the references. Thank you very much for your attention.